One of the largest differences I see between experts in data science and the more unexperienced ones are the ability to debug models and debug use cases. Debugging can be done either because the training does not converge. It could also be done because the accuracy is not what you require for the use case. And finally, it can also be done as a proactive measure to make sure that the models you build are robust, predictable, and fair to all the users. A typical workflow can look something like this. Although it is almost never as linear as this is drawn on the whiteboard. But the point that I really want to make here is that even though we have debugging and evaluation often performed at the end, we need to consider the whole system all the way from a use case to that the algorithms and model is trained, to be able to break down and analyze the different error causes. So what we need to do is to list all the different causes for an error in a non-overlapping way, and then systematically break down and test each one of these. So the debugging and evaluation phase, that can for example include things like residual analysis. We look at what data samples are we doing good on and what data samples are we performing worse on. It can also include sensitivity analysis. So we can try to change the value of one feature at a time and see how that affects the model predictions. And we can also have other ways here, like trying to overfit a tiny data set. So that is often a very effective way once you start the training. Instead of waiting for a large data set to finish to see your accuracy, you make sure that there is no bug in the training script and so forth, and that you have the capacity in your model to overfit at least a tiny data set. Once we have identified some errors, we need to look back on all these other stages and see what can we do to improve it. Normally we break down errors in two different categories. We have irreducible errors and we have reducible errors. And the reducible errors can be further broken down into bias and to variance. So what you often might hear is that reducible errors are the one that we can affect. We can make changes to reduce those, while the irreducible errors are not possible to reduce, just as the name say. But this is not at all correct. The only time this is true is if you are locked into this tiny circle of experimentation with algorithms. And that is something I see a lot of data scientists doing, that they focus way too much on just the model, the architecture of the model, and perhaps the training scripts. Well, in fact, we also need to consider the feature extraction, the data, and the whole use case, how we get the data. So in this circle, we basically have the reducible errors. We try to make better algorithms, better training scripts, better models. So that could, for example, be that we want to identify if we have a model that is overfit or underfit. If the model is underfit, then perhaps the model does not have the capacity to learn the mapping we might need a more complex model or an ensemble model, for example. Or it might be that we have a model that is underfit, a model that is overfit. And in that case, the solution might, for example, be to use regularization. But that was the reducible errors. So what about the irreducible errors? These are, in my opinion, much more interesting in most cases. So the data that goes into the experimental phase with the model and algorithms, that is our features that we have extracted. So if the information to do the predictions just simply isn't in those features, then perhaps we can do the feature extraction in another way. We can look at things like feature crosses, or doing embeddings on text, for example. Just looking at different ways that we can represent the data and making sure that our features are non-destructive of the data that we actually need, so we don't lose any information from our data set to our set of features. If this is still not enough, then we need to go back to the data exploration phase. And here we can tie back to the residual analysis and look at the samples that we failed on. What kind of samples are these? It might, for example, be that the data quality is bad. It might be, if we have images, that we have an incorrect gain parameter set. So some images are overexposed and underexposed, and it's impossible to see the correct thing in them. If we have tabular data, it might be that some column is missing on some samples, or that we have invalid values. But it could also be the labels, the annotations. Let's say that if we have images which are annotated with bounding boxes or poses, perhaps the annotation is simply incorrect on some of the samples. And that, of course, makes it much harder for the model to learn. So we need to think about how is the data annotated and what is the overall quality of the data. Have we done any automatic mining of the data, or is it people who have created the data? And what is the source of the data, and how much can we trust it? If this still is not enough, if the data we have is not good enough to make the predictions we want, then we need to go back to the use case. And unfortunately, in some cases, this is not possible. If you just get a requirement specification, here is a data set, here is what we want to achieve, then this might not be an option. But in most cases, we have a use case where we have a goal that we want to reach, and exactly how we reach the goal is not set in stone. So it could, for example, be that we have not the right data sources. We should collect other types of data. We should use other kind of sensors. Or it might be that the noise levels are too high. We are trying to predict something that is just hidden behind all the noise. And then we need to do something about that. So one example I have experienced here is that I want to, in an apartment, predict or detect if there is a window open somewhere in the apartment. And I might try to do this using temperature sensors in the apartment and humidity detectors or sensors also located in the apartment. And this might work most of the time. Most of the time, perhaps you can see that the temperature is dropping in a certain way when someone opens a window. But it might turn out that in some cases, it's just not possible to make that prediction from the information that we get from these two sensors. For example, let's say that it is very stormy outside, and an apartment is never hermetically sealed, so if it is very windy outside, then we will have an increased airflow within the apartment too. And that might be impossible to, with these two sensors only, discriminate this from the case where window is opened and it is less windy outside. So then we need to reframe our problem. The goal is still the same. We wanted to predict if the window is open. We could do it by mounting magnetic detectors on all the windows. That would be very easy from a technological point of view, but it would be much work to mount all the sensors, and it would be an expensive way since we need a lot of sensors. So another way might be to put two temperature sensors in the same apartment. Then we can get more information and we can measure what is the temperature difference between two different rooms. Another way is to put an airflow sensor on the ventilation, so we can see if the airflow through the ventilation is actually increasing very suddenly. And another option, which does not involve changing the number of sensors we have in the apartment, would be to use a weather service to, at each point in time, get the current weather in the location of the apartment. So we can see, is it stormy outside? Is it very cold outside? Is it a hot day? And so forth. And that wouldn't cost us anything in sensors, and it wouldn't cost us anything in installation time and resources. So that would be a typical scenario of reframing the problem, to try to reach our goal in another way. It might also be that we're trying to use a camera to predict something. Let's say we're trying to use a camera to predict is a door open or not. And it turns out that the resolution is just too bad. If a human looking at the image cannot tell is the door open or is the door closed because it is too far away from the camera, then it might not be possible for the algorithms either. So in that case, we could either move the camera to a close location. We need to run some experiments then and make some kind of guidelines where should the camera be mounted for this to work. Or we can change to a camera with higher resolution and better image quality, which will give us more information to work with. So the key point I want to make here is that when you do the debugging or evaluation, you need to break it down into non-overlapping categorizations that you can focus on one by one. And you should not get stuck in looking in a single area for improvements when the low-hanging fruit might be some other place.